So we had seen the basic operational amplifier and the characteristics and the different types of configurations, open loop and closed loop configurations. In the previous lecture or the previous hours, now we will see some operational amplifier applications. So we can use this operational amplifier in different circuits. So some important applications I am going to share today or share with you in this course. And of course, operational amplifier is the most commonly used element or device in the industry. So you can apply that in a lot of applications actually. So we cannot cover everything. So we will see some important circuits um, that you need to know. Before we see the applications of operational amplifiers, you must have a good knowledge and understanding of the basics. That's what I have talked in the beginning. The configurations, the open loop configurations and closed loop configurations. What will happen if you apply the input to the negative input terminal? What will happen when you apply the input to this positive input terminal? Or what will happen when you apply input to both input terminals? And also you should know the virtual ground and virtual short concept that we are going to apply in all the way in all the circuits. And also you should remember the formula for voltage gain in both configurations, inverting operational amplifier with negative feedback and non-inverting operational amplifier with negative feedback. So if you know those things, then only we can build further the building, the knowledge. Okay, so far we had seen already the differential amplifier. How can we use the operational amplifier as a differential amplifier? Whenever you apply two input voltages, it amplify the differences between these two input voltages. That's why we call op amp or operational amplifier as a differential amplifier. You should know that this is different from differentiator. So we are going to see another circuit. It's called differentiator. This is totally different from this differential amplifier. And another circuit we have also seen already, that is the voltage follower or buffer. The voltage follower or buffer, we are not using any input resistor or feedback resistor. We are just only giving the negative feedback and applying the input to the positive input terminal. And because of this virtual short concept, so whatever the voltage appear at the input, it will appear at the output. This voltage follower is very helpful to isolate two different circuits, because in some cases during the circuit design, when you take the output of one circuit and apply that output as an input of another circuit or input to the another circuit, there will be some loading problem or impedance mismatch problem. So in that case, we can use this operational amplifier as a buffer in between. So it will isolate them and avoid this loading effect or loading problems. So now we are going to see some new topics that is called summing amplifier. The first one we will see, and the second one is integrator. We will see that how it works, what is the circuit construction, and how can we build the circuit and how it works. And also we will see the differentiator, and we will see the comparator. Comparator I have already explained to you slightly. Now we will see the comparator with little more detail. Okay, now we will start with the summing amplifier. So the purpose of this part of the lecture is to introduce the important applications of operational amplifier by providing some background functionality and knowledge relevance to electronic circuit designs. So you can make these electronic circuit designs by using operational amplifier for certain function. Okay, summing amplifier. So summing amplifier is same as the inverting operational amplifier, and a non-inverting operational amplifier. So inverting amplifier. So here you can see the circuit diagram of inverting op amp and non-inverting op amp. So here we have one input terminal is grounded and we are applying input to one terminal that is a negative. So this is called an inverting, and we are getting single output. Here also one terminal is grounded and we are applying input to the other input terminal, which is positive or non-inverting input terminal. So we call this as a non-inverting operational amplifier. So here in summing amplifier, so it can be an inverting summing or non-inverting summing amplifier. So where you are applying the input depends. So in this case, this is called inverting summing amplifier. So here we are applying input to this negative input terminal. And here we have multiple inputs, more than one input. So the other terminal is grounded. So here we are applying multiple inputs to either inverting input or inverting input or non-inverting input terminal. So here you can see whatever the voltages you want to add, you want to sum, you want to perform some addition operation or sum, make the sum operation. You have to apply those voltages to this either of this input terminal through the input resistor. So here V1 is applied through this input resistor R1, V2 is applied through this input resistor R2, V3 is applied through this R3. So everything is going to this single input terminal, which is negative input terminal of this op amp, and we are taking fraction of output and feeding back to this negative terminal because this is a negative feedback through this feedback resistor RF. This is the circuit construction of the summing amplifier. So we will see how we are going to apply these multiple inputs and how can we calculate the output. So as I said, like multiple inputs V1, V2 and V3 are applied through this R1, R2 and R3 respectively. And now let us assume currents I1, I2, I3 is flowing through these resistors R1, R2 and R3. So here we can say I1 is flowing through this input resistor R1, and here the input voltage is V1. Here input voltage is V2, current I2 is flowing through this R2 resistor, and current I3 is flowing through this resistor R3. So we have V1, V2, V3. And here we have the node. This is the node X, where there is a meeting point of input resistors and the feedback resistor. And the other input terminal, that is a positive input terminal, this is grounded. So it means the voltage potential or the voltage amount of voltage at this point or this node is 0. So because this is grounded, and we have a single output. So IF is the current flowing through this feedback resistor. So that is what mentioned here. And we consider this op amp as an ideal op amp. So this is not a practical op amp. This is an ideal op amp for the derivations. So node X is the meeting point of RF and other resistors. And here you should remember virtual ground and virtual short concept. This is grounded, this terminal is grounded. So this other terminal is also virtually grounded or virtually short circuited. So whatever the voltage appear here, it will appear here also. So this is the node X. So the voltage potential at this node is called Vx. So this Vx is equal to 0 based on this concept. Okay, now we will move on. Yes, remember about virtual ground. Whenever we give negative feedback in the operational amplifier, that is the condition, then there will be virtual short exist between this inverting input terminal and non-inverting input terminal. Whenever we give a negative feedback, there is a virtual short between this terminal and this terminal. So if one terminal is grounded here, this terminal is grounded, then the other terminal is also virtually grounded. So voltage potential Vx is equal to 0. So I think you are very clear about this concept now. So now we will derive the equation for the output. So now again we apply the KCL at node X. So I1 plus I2 plus I3 is equal to IF. That is the Kirchhoff current law. Based on the Kirchhoff current law, this is we are applying to this node X and we are making this equation. So now we have to find the I1. What is the value of I1? So again, we apply this Ohm's law, V equal to IR. V equal to IR. So we are calculating I, that is V divided by R. So what is the voltage in this branch? So that is the voltage or potential difference between these 2 points. So here the input point. So here we are applying V1 and here this is the meeting point, that is the Vx. So V1 minus Vx divided by R1. So Vx, we know the value of Vx is 0 and I2 is the same, V2 minus Vx divided by R2. So V2 minus 0 divided by R2. And similarly, the same I3, V3 minus Vx divided by R3, that is I3. So now we know what is I3, I2, I1. So we are just applying this equation. And what is IF now? So IF is also the same. So the potential difference divided by the resistance, the resistor value. So here, what is the potential difference? Vx minus Vout divided by Rf. So Vx is 0, Vout is as it is, minus Vout divided by Rf. So now we have the complete equation. So just 0, just ignore this 0. Now V1 by R1 plus V2 by R2 plus V3 by R3 is equal to minus Vout divided by Rf. So now we keep this V out here. I take the minus and I just multiply everything by Rf. So Rf by R1 multiplied by V1, you can see here. And then minus is the common. I just take it as a outside of this bracket. And similarly, Rf divided by R2 multiplied by V2 or V2 times Rf by R2. And similarly, Rf by R3 times V3. So now we get the equation for V out. So this is, we can consider this is the equation 1. So for a normal inverting amplifier, if we apply single input, then the output will be what? So this is the this is the inverting operational amplifier, right? So we are applying the input to this inverting input terminal. So we have already derived or we calculated the formula for this inverting operational amplifier with negative feedback. So the formula is V out is equal to minus Rf by V in. So if you remember correctly, I told you A is equal to minus Rf divided by Rin. Sorry, Rf divided by R1. R1 is actually Rin. A is what? A is V out divided by V in. That is what A is equal to minus Rf divided by R1. So what I did here is just I keep the V out here and V in I just bring to this side of the equation. So that is how I got this equation. So V out is equal to minus Rf by R1 times V in. So whatever the voltage you apply at the input, it will be multiplied by this factor. So we saw the example 2 kilo ohm, 1 kilo ohm, and we applied 1 volt input and we got output as the 2 volt. And we also saw another example 4 volt. So this is the case for inverting amplifier, normal inverting amplifier with negative feedback. So here, instead of applying the single input voltage Vin, we are applying multiple input voltages. So here you see, instead of I apply just only Vin here, I have 3 branches, and each branch I am applying 3 different voltages. So maybe I apply V1, V1 can be 1 volt. I apply V2, it can be 2 volt, and V3 I can apply maybe 3 volt or whatever, or I can apply same 1 volt in all the terminals, all the input terminals. So it's up to the user. So whatever the voltage we apply, we are going to get the summation of these input voltages at the output. So we will get the algebraic sum of individual input voltages at the output. That is why we call this as a summing amplifier. So now we will see. Let us assume R1 is equal to R2 is equal to R3 is equal to R. What it means? So for example, I apply 1 kilo ohm here. I put the same resistor value here also. So I apply 1 kilo ohm in the R2. I use the same resistor value for R3 also. This is also 1 kilo ohm. So all the 3 resistors are equal. So that is what I mentioned here. R1 is equal to R2 is equal to R3. So we can just consider simply as a R. All resistors are same value. So I think we saw the voltage output voltage formula is minus Rf by R1 multiplied by V1 and so on. The same formula we are taking here. Rf by R1 times V1 plus Rf by R2 times V2 plus Rf by R3 times V3. So since all the Rf and R1 values are going to be the same, all the R1, R2, R3 are same. So what is going to be here? Rf by R, Rf by R, Rf by R, right? So now I am taking this Rf by R as the common outside of this bracket. And I have V1 plus V2 plus V3. So that is what I am putting in this bracket. So minus, don't forget the minus is important. Minus is the common one. I keep this minus always outside these 2 brackets because this is inverting input terminal. So whatever the input voltage I apply, after adding or after amplify, the output will be 180-degree phase difference. So that is why we are having this minus always here. So now we will make another assumption. This is the assumption 1. Assumption 1. So many A, so maybe I don't write A again. So this is assumption 1. And here I make another assumption. What is the assumption? Rf is equal to R1. So this is also 1 kilo ohm I apply. So then Rf is equal to R. It means what? R divided by R, you can cancel. So there is going to be just 1. So minus 1 multiplied by these things are the same. So minus V1 plus V2 plus V3. So if you use same resistor values in all the input branches and the feedback branch, then you will get algebraic sum of all the applied input voltages at the output. So minus V1 plus V2 plus V3. So this also you can experiment in the lab. So you can apply multiple input voltages to this terminal, input terminal, negative input terminal. And for maybe you can apply 1 volt, but here voltage is not a matter. It doesn't need to be the same. Only the resistor values should be the same. 1, 1, 1, 1 here in this example. Input voltages, maybe you can, if you apply 1 volt, 1 volt, 1 volt, then what should you get at the output? You should get 3 volt, minus 3 volt because of minus here. So if you apply maybe 1 volt, 2 volt, 5 volt, then what should you get in the output? 1 plus 2 plus 5, 8 volt. And here I put the minus sign again because of this input terminal. Input is coming to this terminal. So that is how this summing amplifier is working. So you can add multiple input voltages and you will get the algebraic sum at the output. This final equation, so that we had already seen. In case if R1, R2 and R3 values are different, then what will happen? So I told you, you can keep the same value here, but instead of keeping the same resistor values, if you use different values, what will happen? That is what we had seen in the first hour of this lecture today. So by changing the feedback resistor, by changing this feedback resistor and the input resistor values, you can control the gain. If you control the gain, you can control the output, right? So here, instead of controlling one input voltage with respect to the gain, we are controlling multiple input voltages by adjusting these values. So I can use different values of R1, R2, R3, and RF. I can change the gain values of each voltage level, and I can get the different output. So by this way, you can scale up or scale down the input voltages. So we can also use this summing amplifier as a scalar. So scalar is used to perform the scaling operation. Scaling means you can scale up or scale down the applied input voltages. The summing amplifier, you can play with resistor values, you can play with input values, and you can check at the output what is happening.